Hello everyone, we are Team 3 and I am the first presentation, Jo Young-jun. This is our weekly study plan. It has flow of foundation, structure, construction, and skin. And we are now studying about structure of Lotte tower. Last week, we studied about two structural systems, gravity resistance system and lateral load resistance system. There are core wall and mega column in gravity resistance system, outrigger and belt truss in lateral load resistance system. This week we studied about more details of outrigger and belt truss and diagrid structure. First, let's see how the outrigger and belt truss work. Let's assume that outrigger and belt truss are installed in this building. When the lateral load occurs, it generates exterior columns axial force, and then it moves to outrigger belt truss, and core wall, and foundation. In the wind direction, tensile force is generated on the column, and in the opposite direction of the wind, compression forces are generated. So the rigidity of the column is included in the horizontal rigidity, which increases lateral stiffness and decreases the horizontal displacement accordingly. The column bound to the outrigger constrain the rotation of the core, thus reducing the horizontal deflection or moment that occurs in the core than if the core exists alone. This is the deflection curve. Red line indicates deflection of structure with outrigger, and dotted line indicates without outrigger. You can see that horizontal deflection reduces when outrigger is installed. Also, the moment reduces. So, outrigger systems increase the flexural stiffness of the structure. They do not affect the reflex that the core bears entirely. We looked into the structural behavior of the outrigger and belt trusses. This time, let's find out more about the connection with the outrigger and belt trusses. We focused on this part, connection between mega column and outrigger. This is the section of connection part. It is mega column, slab, bottom chord, and outrigger diagonal. For the design of the connections between the outrigger members and the mega columns, it was intended that an outrigger diagonal member and a horizontal member be connected at a column embedded connecting post as shown in the slides. Horizontal forces to the outrigger diagonal member are supported by the bottom chord. And also the top chord supports horizontal forces to the diagonal member. At the wall corners, to support vertical force of the outrigger diagonal member, a vertical post is installed at the top and bottom of the outrigger member. Next is about belt trusses connection. We focused on connection between mega column and belt truss. This is the picture of belt truss construction. We focused on this part. This is a mega column. On the outside of the mega columns, there are embedded plates to connect trusses. These trusses are pre-assembled and mega column and trusses are connected through the field welding. If you see these parts of belt truss in upper side, you can get this section. To reduce deformation of the 14.4 meter high embedded plate caused by axial loads and to design proper dowel bars. Shear transfer bearing plates are needed in every space between dowels. And it was assumed that cracks would occur at the edge of the embedded bearing plates in the mega column. Therefore, the The embedded plate is installed on only one side of the megacolumn, but in some floor levels the plate would enclose all four sides of the megacolumn. Through this connection of belt truss, if the belt trusses supporting the hotel columns are installed along the outside of the megacolumns, the megacolumns can be constructed continuously regardless of the belt truss construction process. And for the last, there's one more detail. It's redundancy. The important members, such as spandrel girders in typical floors, belt trusses, and hotel steel columns, have redundancies. To avoid a sudden collapse when one of these members loses its capacity in case of fire or unexpected impact. So, it means no matter which column fails, the important members does not collapse suddenly due to the redundancy.
I'm the next presenter Jaesuk Choi, and I'm gonna tell you about diagram structure. Looking at the structure of Lotte Tower, the belt truss and outrigger are applied until the 107th floor. From the 107th floor to the top floor, the diagram form of lantern is constructed. This picture shows the uppermost part of Lotte Tower. This part is diagrid. Then, what is diagrid? Diagrid is compound word of diagonal and grid. Diagrid is an exterior structure system that all vertical columns are eliminated and consist of only inclined columns on the facet of the building. A structure system that is single thickness in nature and gains its structural integrity through triangulation. Diagrid system saves approximately 20% structure steel weight when compared to a conventional moment frame structure. In other words, it is an efficient structure that can resist lateral loads while reducing its own self-load. So, diagram system is applied in Lotte Tower. Before explaining the principle, we will first look at the actual construction. This picture shows the diagram being constructed. It's almost the top part, and please focus on the triangle structure. This is the node part of diagram, and I will explain it later. Lotte ENC made a diagram connecting large steel pipe, which made by rolling up a 6 cm thick steel plate in shield shapes. That one member has a height of 11.7 meter and a weight of 20 tons. Since the height of one floor of Lotte Tower is 3.9 meter, 4 to 6 are installed over 63 floors. Then now, let's take a look at how the diagram is loaded. This shows a section of diagram. First, when the lateral force is applied like this, the tensile force and compressive force act to show resistance to the axial force. Also, when the axial force acts like this load is distributed through the member and transferred to other connected diagram. This is why it has a high resistance to lateral loads. Also, this diagram is connected with the belt truss on the 107th floor, the outrigger on the lower floor, and the belt truss. It resists axial force together. Through this, Lotte Tower are equipped with a wind resistance and earthquake resistance design that can withstand an instantaneous maximum wind speed of 80 meters per sec and an earthquake of magnitude 9. This is the whole principle of Lotte Tower's lateral force resistance system. However, this diagram also has consideration while designing. It can be divided into two considerations. The first is the angle of the diagram, and the second is the stress concentration of a specific member of diagram. First, let's take a look at the consideration for the angle of the diagram. Members that arrange diagonally receive their respective shear force and bending moment. Depending on the angle, the levels of force is different that apply to these members. Therefore, there is an optimal angle that properly affects these members, and it is different depends on the height of the building. They decide that 60 to 70 degrees is the most appropriate. Second, it is a stress concentration phenomenon that occurs at the node of the digrid. Enlarge the part where the digrid of Lotte tower connects. The following junction exists. First, the components of junction of the node are as follows: end plate, node lip, circular tube, and web stiffener. Among these, the stress is concentrated at tube, end plate, and lip part. When a force is applied to this junction, stress is transmitted from the upper tube to the previous same components, and then to the lower tube. During this process, stress concentration occurs in the end plate, node lip, and circular tube. This picture shows the degree of stress concentration in the experimental results. To solve this, the end plate should be reinforced mainly to prevent the destruction of members that subjected to this stress concentration. Finally, let's take a look at the difficulties in the construction process. As we mentioned, a digrid was installed at the top of the Lotte tower. Difficulties in the construction process are mainly due to work on height. Therefore, the tower crane should be installed first to carry out these works. This is a video of the tower crane installation process. At such a high altitude, workers had to proceed crane installation work in the air. The details of the crane will be covered in the construction part in the following week. Just installing the tower crane didn't mean every work went smoothly. Due to the height of work site, the effect of wind was unavoidable. Due to the wind blowing in real time, it is necessary to coordinate location of digrid in real time. So, GNSS system and simultaneous measurement of vertical angles by 4 satellites and clinometer measurement are applied during construction. This is our role. All of our members did researching and making PPT. Yerim, Hyunmin, Inchang made a script, and Youngjun and I did presentation. Thank you for listening.